Welcome to MarineLearn, practical knowledge and training for maritime professionals. Hit the bell button, subscribe, and like the video so we keep bringing valuable content to you.
Welcome to Module 2. Today, we are going to examine the science of shipboard metals and the core principles of mechanical craftsmanship. A ship operating at sea is an isolated, closed ecosystem. Every component inside the hull is subjected to extreme kinetic forces from the ocean, severe thermal gradients from the boilers, and the constant, aggressive reality of saltwater corrosion. To keep a vessel operational, you must master these 4 mission objectives. First, we identify the metal's baseline properties. Second, we decode ferrous metals, tracing the carbon scale. Third, we navigate non-ferrous alloys, mapping the copper family. Finally, we apply these to specific naval applications. When a part fails in the engine room, replacing it is never as simple as swapping out one piece of metal for another. Survivability depends entirely on your ability to accurately read the original material's operational limits. The ship's anatomy features 3 distinct metallurgical systems. The skeleton and muscle uses high-strength ferrous metals for structural integrity. The circulatory system relies on highly conductive, corrosion-resistant copper alloys. Finally, the skin and nervous system utilizes aluminum, tin, lead, and zinc for lightweight protection. Every system requires a highly specific elemental family. The physical threats in the intense heat of the boiler room are distinct from the threats encountered on the main deck, requiring specific materials. This infographic breaks down the baseline physical properties of our materials. Fusibility, or the exact melting point, and specific gravity, which measures the metal's weight relative to water, form the baseline metrics for determining where an alloy can be applied in an engine. This diagram illustrates the core mechanical properties. On the top left, ductility allows a metal like copper to be drawn out in tension without rupturing. On the top right, malleability allows a metal like lead to permanently extend in all directions when hammered or rolled. On the bottom half, we see tenacity, the ability of mild steel to resist tensile forces without pulling apart. This contrasts with elasticity, a metal's power to return to its original shape after a force is released, like a heat-treated spring. This comparison shows 2 distinct microstructures. A metal's visible macroscopic reaction to physical stress is entirely dictated by this internal crystalline architecture. Look at the wrought iron on the left. It contains pure iron crystals interlaced with dark slag threads. When struck by a heavy impact, these threads absorb kinetic energy, allowing the iron to bend under shock rather than break. Now look at the cast iron on the right. Its matrix is made of sharp, rigid crystals. It contains no slag threads to absorb impact, creating a highly brittle structure. It cannot permit distortion, so under heavy shock, it shatters. Understanding a metal's internal microstructure is the only reliable way to predict if it will bend or shatter under sudden kinetic marine stresses. This diagram traces the ferrous-carbon continuum. Carbon acts as the master dial in metallurgy. Adjusting the carbon percentage transforms raw, smelted pig iron into the highly specialized components required for marine engineering. Starting on the far right, keeping carbon extremely low, around 0.02%, yields wrought iron. Moving toward the center, increasing the carbon up to 1.5% creates plain carbon steels, which form the backbone of hull mechanics. Pushing the carbon dial higher, between 2 and 4%, yields cast iron. The high carbon content makes the metal brittle, but also makes it dimensionally stable and easy to cast into complex shapes. This matrix details the distinct types of cast iron. Gray cast iron, shown in the top left, is easily machined and highly stable after aging, making it perfect for heavy machine bases. White cast iron, on the top right, cools extremely fast, creating an exceptionally hard, brittle surface, used for applications requiring maximum wear resistance. This comparison highlights 2 heavily utilized structural metals. Because wrought iron on the left is fibrous and shock-resistant, it is exclusively forged for crane hooks and chain links. Conversely, the plain carbon steel on the right scales dynamically in strength based on its exact carbon classification, providing the rigidity needed for drive shafts and structural I-beams. Tuning that exact carbon percentage is what allows engineers to balance dynamic shock resistance against rigid structural load-bearing capacity. This diagram outlines the copper foundation. Stepping away from the rigid structural strength of ferrous metals, pure copper provides exceptional thermal and electrical conductivity, making it the primary base for shipboard electrical networks and heat exchangers. The alloy tree shown here illustrates how adding zinc to copper creates brass. Altering the precise zinc ratio generates a wide spectrum of properties, ranging from highly ductile cartridge brass for severe deep drawing to rigid, heavy-duty naval brass. Conversely, this second alloy tree demonstrates that alloying copper with tin creates bronze. Crucially, introducing tin is what actively prevents saltwater corrosion, making bronzes vital for submerged components. Notice the gold box near the bottom. Admiralty gunmetal combines copper, tin, and zinc to create a fine-grained, pressure-tight structure. This specific formulation makes it the paramount marine alloy for vital saltwater pump and valve bodies. These specialized non-ferrous elements provide localized protection against distinct chemical threats. Lead resists highly corrosive battery acids. Tin provides a corrosion-resistant coating and acts as a soldering agent. Zinc serves as the ultimate sacrificial armor, used exclusively to coat and protect galvanized iron sheets. This scale demonstrates the extreme density difference between aluminum and steel. Aluminum possesses low tensile strength compared to steel, but it offers a critical 2.5 times weight reduction. This makes it indispensable for constructing lightweight superstructures, where minimizing topside mass is necessary. Non-ferrous materials deliberately sacrifice raw structural strength to conquer the unique chemical, thermal, and weight challenges of the ocean environment. The diagnostic matrix on screen is the engineer's primary tool for cross-referencing material properties against specific operational threats. We will use it to navigate 2 practical scenarios. Here is scenario alpha. You're fabricating a replacement chain link for a main deck crane subjected to violent jerking and heavy impact. Gray cast iron shatters under impact. Aluminum lacks base tensile strength, and cartridge brass is the wrong elemental family. The only correct option is wrought iron. Choosing wrought iron relies entirely on understanding its internal fibrous microstructure. It is the only metal on the board capable of safely absorbing and bending under sudden kinetic shock without rupturing. Scenario beta. A saltwater cooling pump requires a newly machined valve body resisting aggressive corrosion and holding high pressure. Plain carbon steel has strength, but rapidly corrodes in saltwater. Lead resists corrosion, but is too soft to contain high fluid pressure without deforming. The correct choice is Admiralty gunmetal. Its exact elemental formulation tightly packs the crystalline structure, making it highly pressure tight, while the addition of tin renders it virtually impervious to saltwater corrosion. This clipboard summarizes our module. Physical and mechanical properties dictate a metal's survival. The exact carbon percentage controls the strength of ferrous metals. Alloying copper handles the ship's chemical and thermal demands, and specialty elements act as highly localized shields. A skilled marine engineer must understand exactly how these metals behave under intense heat, pressure, vibration, and seawater conditions.